Alright, time for another draftphysics.com, debatephysics.com, also video presentation. Anyway, so over and over again, just keeps going on and on. Yeah. So what we're looking for is evidence to prove physics has integrity, that what they say is actually true. Now, on the website, I have the subjects of gravity and I don't think I have electricity, but I have charge, which is the important one. And kinetic energy shows up. Energy, the idea of what is transferred between objects in the universe. And frankly, the Descartesian notion that this stuff called motion or energy just moves through the universe. It's always somewhere. There's no rest for energy. It never ceases to be used up, frankly. It just doesn't get used. It only goes through transitions. And frankly, and those transitions tend, to be from organized, that is, everything going in the same direction, to energy that's dispersed, that is, it's going in all kinds of directions. And so basically that's our use of energy. But in the universe, it really doesn't care about direction. So the universe stays the same temperature, so to speak. Anyway, in substance, I don't want to get into all the nuclear bits because frankly you can put energy in terms of just organizing atoms. And in organizing atoms, what you're really doing is organizing electrons and protons. And that is the key to the whole, make it very, very small because you made it very organized. And then as soon as you disorganize it, it gets very, very big. That's energy from our perspective. So anyway, usable. So they have this kinetic energy theory, 1/2 mv squared, and what it means is they're claiming it takes 25 times the force or fuel, to make something go 5 times the velocity. So 25 times the fuel to go 5 times the velocity. Now, the best way to understand this is the spinning arguments, because then you can evade all of their relativity nonsense. And Newton sort of proved that with a spinning bucket experiment that they don't have a real viable counter argument for. And in the notion that this relativity argument kind of breaks, that is the idea of not understanding what thing is actually moving. You do know which thing is actually moving when you spin it, because the idea that the entire universe spun is idiotic, besides the fact that it's impossible, because spinning the universe won't make the atoms move out. So, Newton did it a couple of different ways. Spinning an object with little weights hanging off of it. You spin it and the weights move out. Well, obviously, it's the motion here, the momentum here, that's real in the spin, that's making the weights move up. Alright, so, it really can't be reasonably defeated. So we have no evidence of this. So this is the big one here. All they need to do is show something like this. Show, I don't care, 16 times the force creating 4 times the velocity, or 9 times the force creating only 3 times the velocity. But it won't happen, because it doesn't happen in reality, because the theory is wrong. Now, I've brought up the lever because Steve Mould brought it up. I brought it up before that, but as an example. And then he just proved my point for me, in the sense that he basically said science says levers don't work, because levers conserve momentum, and you don't conserve momentum in their physics. And so there's just this simple argument about what actually equals what. Now, if you use a balance, that is, use a lever as a balance, you can put a 4 mass at one distance, okay, and you can have a 1 mass, okay, at 4 distances, and those things will obviously equal. So 4 times 1 is the same as 1 times 4, because the velocity is equal to the distance. Okay, so that's the law of the lever, the indirect consequence of the lever. The law of the lever is just saying, look, you just multiply the distance times the mass, and that defines how much weight you have. And clearly the distance is momentum. The distance is a change in velocity, and that's the simple truth of it. So it works in gravity, or it works this way also. And that's experiments tempting to get to this. And so what you need in the experiment is obviously a constant force. So this idea of a lever launcher, where you have a spring at one end, and then you would just launch objects at the appropriate distances. So that's in this case a 2 mass at one distance, or 1 velocity, okay, versus a 1 mass, okay, at 2 velocity. Now they say it doesn't move at 2 velocity. They say there's some kind of inertia problem. And as I pointed out, there's obviously no inertia problem, because guns maintain an equal momentum, no problem. They don't do the 1.4 thing. Guns shoot bullets. They conserve the momentum. The very light thing gets all of its momentum. The very heavy thing gets all of its momentum, the other half. No problem. And so this notion that, light things can't be propelled at a half mass, can't be propelled at twice the velocity with the same force. Conserving momentum. And obviously the lever presents another problem for their physics, because they keep talking about how direction matters, and obviously you can, you could put a 4 mass on this side, and you could drop a 4 mass on that side, and you have every expectation that you're going to get all of your energy, but you're going to get it in the opposite direction. And there's not going to be any reasonable explanation. This idea that somehow the whole Earth moved with twice the velocity in the opposite direction is just nonsense. Okay, again, no evidence. All right, so they think they're doing these really, crappy, cheap, cruddy experiments, and claiming they're proving something. And then I'm pointing out how there's all kinds of flaws in their reasoning in the experiment, and they find that as evasion and denial of their perfect analysis and reasoning. And it's just obnoxious on their part, frankly, because it is true that there are all kinds of variables. So I will pause to erase and then go through some experiments I just thought of, and then we'll go over some of the flaws in their reasoning. Alright, so even though it's been shown over and over, that pulleys conserve momentum. You have 2 ropes on one side, 1 rope on the other side. Obviously the 2 ropes, move more, there's more distance caught up in the 2 ropes moving than in the 1 rope moving. They both will have to have the equal amount of movement. So obviously with 2 ropes adding rope, you're going to have less movement than if you have just 1 rope with all of that movement in it. And so it's a perfect example of conservation of momentum. And then you can just balance. Like I said, I can just create a balance, a 4 mass and a 1 mass, 4 units of distance, same thing. If I rotated it, I would end up with the same energy on both sides of the rotation. There's no way to avoid that. And it would have the same energy as if I just had 2 4 masses. So I thought of an experiment that sort of duplicates the Newton's cradle thing, just because it'd be sort of interesting to see. So you put a little steel ball, 1 mass. And the only, in one case you have a 2 mass. I guess I could make that another color just to identify it as different. So we have the 2 mass here. And then we have a 1 mass on this side. So we have 2 balanced spinning objects. And then all you're going to do is put a force in this way. Obviously it's going to be a Newton's reaction thing. this thing will spin all the way around, take all of the energy, come back and hit this one, and then this one has all the energy. It'll spin all the way around. And I'd just be curious to see how well it worked. I mean, obviously it's going to tend to process and they'll start missing each other. But it'd be an interesting experiment to see how long it lasts or how long it works. But obviously there'll have to be the same energy in both. And it'd be another example of conservation of momentum. So every time I say the word energy, the game is ruined because they've stolen the word to mean kinetic energy, to always put kinetic in front of the word energy. And obviously I'm using the term as Newton would have used it if it was coined by then. Instead of saying quantity of motion, they would have said energy. Descartes would have said energy, even though they were believers in momentum explicitly. Let's not forget Newton said, twice the force, twice the velocity, 3 times the force, 3 times the velocity. Defining, frankly, force as momentum. Directly equal, frankly. How much momentum does the force have? That's how much force it has. Anyway, so that's one experiment. So let me go through. Do I remember the second one? Well, we'll see if I can remember it. Alright, so I'm just kind of hopeful this video works. Lots of trouble. My computer crashed out, so I had to use one I got in the garbage, and then it didn't work, and so I had to finagle parts and whatnot, but it seems to be working now, so hopefully it will continue to do so I can make these videos to the charming audience of trolls and jerks. Anyway, so what we're back to just this idea of the ideal circumstance is to have to hang a lever from the top, so that way you do have a balance. And so this would be up, okay, the ceiling, and this would be down. And the idea would be to create a mechanism that has no friction in it, if possible, so have it suspended in air. And again, the idea is just going to be to do this simple thing where you just prove that the 2 mass at the half the distance is somehow will conserve momentum, but the 1 mass out here won't, because somehow inertia won't allow it to go twice the velocity. So you won't get 1 velocity here and a 2 velocity here with the same force put in. So you do these 2 experiments is frankly the idea. And so the idea is if you hang it, then you're assuring the balance first. You can see that you've got the weights in the right places, and then you just give it a spin with some kind of force. And that's the tricky part. Now I thought about, well, the fact is if I give it a spin with a force, it's going to tend to move the whole lever. And so I like this little idea of having a magnet here, a little north-south magnet, at this end, and then a little magnet here, and have a distance separating them, and have this tied to the ground, and so that way it can't go off its center. But the neat thing about magnets is when you have 2 on a string like that, they don't have any torque when they move, they spin. So you can spin magnets without any torque, no friction, in other words. So that'll assure that it stays in its position and rotates instead of migrates. So I thought that was a good innovation, but we'll see what I get around to doing. Doesn't seem very complicated to make 2 of these and just use magnets to hold the masses on, and make sure they dangle from this object. They're free to move. So, and that way you'll ensure that the energy stays in the mechanism. Anyway, yeah. So those are those 2 ideas. So now we'll get to their experiments. that the pieces of them that are just they need to be understood as being potentially catastrophic flaws. Yeah, they just won't pay attention to those arguments. Alright, as this bar essentially showed, and once you have your device built, it's really easy to make modifications to it, and the experiment, boom, boom, boom. You can do like 10 of them in 60 seconds, 10 experiments. So in some of these cases, there's really no excuse not to modify locations of timing gates, different things that you could modify to do the experiment better, and at least provide a deeper proof if you think it's going to prove. Alright, so the Despard experiment is basically, I think he's still using a rubber band. Alright, so you have this rubber band, okay, creating your force, the same force, and you're just going to pull this thing back. Now, as I pointed out, he has a stop here, okay, and so you pull it back to the same place each time. Now, instead of pulling his lever back where the stop is, he's pulling it back over here. So obviously that means you could bend the lever a little bit. You can put an unequal amount of force on it. And so what he should have done is put his little string here and pulled back and then cut it. And then he'd have a more guarantee that he couldn't put any bending force or any extra force in because he's against the stop. And have a very rigid stop, of course. This, we don't have any idea what his fulcrum is, so can't say much about that. Alright, so another thing he did, well, he stated that his timing gate is at the peak velocity, and no, it's right after liftoff. So this is going to swing this whole distance, and he has the timing gate right here at the beginning. So he certainly should try the experiment also from different locations. Now, the most glaring thing that he's doing in the experiment is he has a tremendously strong spring, and this all happens really fast. So there's really no need for it to go supersonically fast. No need at all. You need a minimum amount of energy, and you want to just stop at enough. You don't want to go to too much. So you want to go enough and then not too much. So somewhere between those two things. And it seems to me that they are trying to do too little or too much. Because it's never just right, from Goldilocks. The speed is never just right. Certainly by my standards. I mean, you're using a timing gate. You want to give the gate the most opportunity to get a right answer. It just seems reasonable. And obviously any defects in the takeoff could be compensated for later on, and so who knows what those numbers would be if he tested the time later in the voyage. Now, as pointed out, he did something, that really isn't ideal at all. So he has these gigantic washers with a hole in them. And then the stick going through is, 1/3 of the diameter of that hole. So if I blow that up, it means it's when it's not moving, that's what it looks like, right? The little stick, the washer hangs down on it. And as soon as I start to move it, what has to happen is this has to rotate up, because now it's going to be pushing essentially this way. So essentially it's going to look like this eventually. As soon as it starts moving, that's what it's going to look like. But the only way it can look like that is it's frankly going to turn the washer and raise it in gravity. So he's lifting the washers, and that energy has to come from the only energy there is, which is this spring, the force. So any motion up has to be used. So, and obviously at the slower speed, there's less of that. So obviously when you're pushing the 2 mass, it's moving slower, so it's not going to be as aggressive in terms of shoving the object up in gravity. Moving it with momentum. I mean, that's the key point, is really, this is again what you can see. So he did a video, just did this stupid mocking crap he does, and he's mocking the whole idea because you can't see it doing this. So he shows the video of the thing moving, and because you can't see the washer rotating, that somehow it didn't happen. So that's just like somebody saying, well, I have a plastic cart with a bunch of metal wheels, and when it's moving, I can't see any angular rotation. I don't see any energy trapped in angular rotation, but you can know it's there. The wheels are rotating, and all of their rotation was consumed by the initial force in. So you've degraded its linear velocity, and the fact is, when it hits something, its momentum isn't going to be its linear momentum. It's going to be its linear momentum plus its rotational, angular, you could argue, momentum of the wheels. So I stopped watching. I mean, there's no point. It's a fact. This is not ideal. It's just a fact. All right. You should probably find some better thing to put on this lever. You're doing a test and you're putting something on the lever that looks like that. I mean, why would you try to have a mass that's as concise and immovable as possible? There'd be no reason to think it's a good idea if the masses slide and move. That wouldn't be a good idea. All right, and I've made this point hundreds of times now, frankly, dozens, let's just say, that in these experiments where you're actually going to push something that's not attached, that you really should have a barrier, okay, to prevent the object from going centrifugally in the wrong direction. Because that obviously, again, the only energy in the system is the energy you're putting in with this device, this spring. And any other motion created, any motion that way, has to come out of the motion that way. So, they're real problems, and they just pretend them away. So another thing Despard did was, he has this lever, and the problem was it would lean, okay, on the fulcrum, because this end's heavy, okay, and so it would tilt down. And so he fixed that by putting a bar across here at some arbitrary location. Who knows how he decided. So essentially, this was happening. It was tilting down, and so he put a bar under it so it would stay level. Now, the problem with that is that on one case, the weight's on one side of the bar, and in the other case, it's on the other side of the bar, obviously creating extra weight. So this is an unknown amount of friction for each experiment, where if he put the bar here, that is, if he prevented this side from going up, instead of preventing this side from going down, you could understand that no matter what weight I have on this side, they're supposed to weigh exactly the same. The 2 mass is going to weigh the same as the 1 mass further out. So there'll be the same friction on the bar. See, these are little pieces of logic that you can apply to understand it does make a difference. I could do it one way that's not right, that is unknown what the actual friction is going to be, or I could do it one other way where I know exactly what the friction is going to be. And they find all of this obnoxious. Okay. And again, they're proving something dramatic. They're proving that a 2,000-year-old law of the lever is a lie. Okay, for 2,000 years they've been not telling the truth, because the half mass doesn't go twice the velocity, it only goes 1.4. They're basically saying that if I give you a ball and I make it twice as light, you can't throw it twice as fast. You can only throw it 0.4 faster, all right, with the same energy. And logically, I can make no sense of it. I mean, I've said it a million times. I'll say it again. I mean, the force is it's collecting on mass, on electrons and protons. You're made out of electrons and protons. And when a force like gravity hits you, it's basically just sticking to the electrons and protons. They're like sticky. So if one hits, it sticks. And so if you have half as many, okay, that means that, the amount of, force you're going to collect is going to be smaller. It's like having a smaller sail in the wind. You're going to collect less wind. But you have less mass to move. So obviously the less mass to move is going to compensate for the smaller amount of force collection. But I mean, it's just that kind of simple, that all this is you're saying if you're going to keep the force the same and reduce the mass, then, the time in the force, you're going to get twice the velocity. All right. Also had allergy attacks. Very hot here also. I guess I'll erase this just to make it clearer. And we'll move on to Falwell. So the dispar point is no need for, well, just try the experiment in something like 1/8 of the velocity you're currently using. I mean, you really don't need to smash everything into the wall. You don't. The experiment should be provable at any speed, and just about. And so that'll be the irony, is Falwell's doing exactly the opposite. He's putting so little energy in that you're not being fair to the experiment because of the vagaries of the frictions that exist in the experiment. And again, so they're debunking such a, wheel balancing. I mean, they're basically saying that somehow, even though you have the same momentum in a wheel, that is, I could spin this little thing here, and I could have a 2 mass in here, and I can have a 1 mass out here, and they're really saying that if I spin that, I have different momentums. If I put two masses and I put 2 1 masses, that somehow I can have different momentums in those objects, when this is going to go twice the speed at the outside. 1 mass is going 2v, and when you have 2 masses going 1v, same thing. You can't make more out of it. You can't make more rotation, or less for that matter, because you have to conserve momentum. So they're arguing with really basic physics, really basic statements, and they won't even fess up and say that's what they're doing. They won't say the words, the law of the lever is wrong, even though that's exactly what they're trying to prove. And that's the part that's just really weaselly about these people. Alright, so let's move on to Falwell's nonsense. Alright, so another context for this whole conversation is the fact that they won't even argue that these experiments need to be done, that this needs to be researched by regular physicists, that, there needs to be a lot more testing of this 1/2 mv squared theory. Okay, and even coming up with that magical experiment showing that 25 times the fuel to make something spin 5 times as fast. That needs to be shown, or that something spinning 5 times as fast creates 25 times the force or impulse. Absolutely no physical evidence that's true. And just, you could just imagine. I mean, obviously I can have a contest and even make it $500 or something for the best experimental blah, blah, blah. But no one's going to see these videos, so it's a waste of time. And so just imagine if Steve Mould, instead of just announcing a fake experiment, one he didn't do, and just saying what the results of it would be, even though he didn't do it, instead of doing that, if he had just said, hey, look, there's some interesting facts about levers, and if he offered the contest, you could literally have thousands of people thinking about it and trying to do good experiments, proving it once and for all. So, it's a dramatically different world if these people would be on the right bandwagon. The bandwagon should be, is science needs to have integrity. They have to have evidence if they're going to argue for a case. Okay, very weak evidence shouldn't make very strong assertions. And that's the part that's really ugly. And they should concede it's ugly and they're fighting on the wrong side. They're protecting unevidenced physics. And that's really... yuck. Yeah, that's bad. Alright, so Falwell has a... so he has what he claims is an equally oiled and slick surface. So like this whiteboard or something. It's a very flat, slick surface, and then he's waxed it or oiled it to make it even slicker. So when he does this launching of two objects, with the lever launcher, alright, that they're in equal conditions. So his spring is really weird. I mean, the whole thing is a little strange, but anyway, this doesn't matter. All right, so the idea is you're gonna push the one mass at twice the distance, the two mass at one distance. So he has real weights, precision weights, which not really of any value. So they're cylindrical and tall. Okay, so this they're like this, and he's hitting them this way. So obviously this is not ideal. I mean, pushing things that are shaped like this across a surface, not ideal. Now they probably have a flat bottom, okay, which is also frankly not ideal when you're trying to make something frictionless. So what you really want to do is have some kind of, you want the smallest contact surface. So ideally the round object would be nice. So if you just put a ball bearing on the bottom and then you just have this little tiny contact point, and that's pretty good. It creates a nice slidable surface. I mean, I guess ideally you could have something pointy and that would be even better. So the less surface you have, it turns out, the less friction you're going to have. So that's what you want to head for, not a flat surface, because that tends to, even on oil, create a vacuum between the two surfaces, so it makes it actually sticky. More stickier than you need, especially with the weights as heavy as these weights are. All right, and so what's he, so first we don't know anything about how slick this surface is, how evenly it's slicked and anything. So what he does is, okay, he pulls back the lever, and what he finds is, okay, when he pulls the two mass back and does the experiment, it goes out with a certain speed. And what happens is when the one mass is going to be at that same distance, and it doesn't move. And he says, it's inertia. That means it doesn't move. I mean, it doesn't move at all. So, I mean, the lever's pulled back and it just stays there. Now, obviously, that's not inertia, because, like, if you're doing it in space or something, it would have to move. Even if there was this inertia thing that was heavier, it would just move really slowly. So we know this is static friction. It doesn't have anything to do with inertia. Okay, it's static friction. And obviously, when you're doing something at over a longer distance, you're applying less force per distance, blah, 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 blah. It's only a one mass after all. So it's just static friction. So instead of just saying, oh, okay, well, let me tighten the spring a little tiny bit until this one does move. Because all you have to do is overcome the static friction. Static friction doesn't cost you anything if you break it. So once you break static friction, you really don't lose any energy. Now, you could also tap on the table, and that might just make the weight jump a little, and therefore it can go. It'll break the friction. But static friction is friction in one location. Obviously, it's not drag friction, so it doesn't add up and accumulate and all that kind of stuff. So it's really not an issue. But regardless, you can get rid of the issue by just tightening the spring. So go to the minimum speed that allows this to move, and then see how fast, okay, now that you've tightened the tension a little bit, how fast the two mass moves. Now, he got all kinds of weird numbers. He put it at this 1.4 distance, the one mass at the 1.4 distance, and made the claim that somehow that's the appropriate distance. But you know that it's all all of these distances will change how fast this moves. We're trying to make the lever move the same exact speed. That's the whole point of the experiment, is to prove the lever moves exactly the same with a 2 mass and a 1 mass. Now I can put it there, but the lever is going to move a different speed. So we've changed the speed the lever is going to move at. And so the lever is going to tend to always get the force that's over here over here. So the fact that, the fact is I can move the 2 mass over and it's still going to go almost the same speed. So it doesn't matter where I put it, it's going to go close to the same speed. You can't change the fact that you're basically putting a force in and you're going to get a force out on the other side. And there's no magical location that I put the 2 mass that, it's magical. I mean, it is a fact that it'll tend to, it'll tend to have a point that's maximally efficient. But the fact is, you'll go, let's say is 17 frames here. It's going to be 16 frames here. There's going to be, or 18 frames here, and 19 frames over here. I mean, it's not going to be that big a difference. So anyway, the whole point is to create the idea as close to the idealization as we can get of a 1 mass going 2v and a 2 mass going 1v, and and the lever moving the same for both, proving it's the same work to move a 1 mass at 2 velocity as it is to move a 1 mass, a 2 mass at 1 velocity as a 1 mass at 2 velocity. And momentum is always conserved unless you lose it to some stupid thing you did. Now the other thing was quite obvious. Even in the big mass, they moved that way. Okay, they moved that way. So obviously you want to get rid of that. And again, the little stick over here would get rid of that problem. And it has to be immovable, not some rubbery stick, but something pretty firm. And as long as it's firm, the energy won't go in. Okay, it won't get used up. And you'll get a better, straighter launch. Alright, but I mean, obviously the single mass dramatically moved that way more. So obviously more energy was going, with the 2 mass. I mean, the 2 mass did this, the 1 mass did this. So obviously the 1 mass was losing a lot more energy to this direction. And such. It's obvious. So obviously in this experiment, there's just no excuse to do it at this minimum amount of energy, so you can't even get this object to move. Theoretically, I would argue that the static friction should be the same for both objects, but that all has to do with us believing that you did the experiment, that somehow you know exactly how slick the surface is and how level it is and how even it is, and I doubt you did any of that. Again, just chicanery. They just keep manipulating experiments to get them to produce the results they want. So it's no different, essentially, than Professor Lewin's clay cart experiment. It's, they're rigging the experiment to do a demonstration of, frankly, something that isn't true. It just isn't. You have to conserve momentum, and as Professor Lewin says, nature doesn't give a fuck about kinetic energy conservation. Again, in all these experiments, they keep saying, "Oh, yeah, the 5-ton train. You add another 5 tons to it, and you have a 10-ton train." You could draw that better. Going 5 miles an hour. So you start with a 5-ton going 10. You add 5. Now you have a 10-ton going 5. Perfectly conserves the momentum, and they say half the kinetic energy was used as heat. Well, how could you make heat and conserve all the momentum? Will they answer that question? Never. They'll never answer the question. Because you can't. You can't do it. Bowling balls lose their velocity when they hit pins. They can't keep their velocity and move pins. And heat is the same thing as moving pins. It's transferring your energy, transferring your momentum. You can't have friction with a surface and keep your momentum. You can't do that. Alright, so I'll take a pause here, but I think we're about done. Alright, so summing up again. So look, this is the big one, the gorilla in the, or the elephant in the whatever, you've got to take notice of. It just doesn't happen anywhere in reality. This doesn't happen. Water wheels, lots of mechanisms, turbines at Niagara Falls, all kinds of places where this doesn't work. 5 times the velocity is not 25 times the force. Making things go faster, lighter, small things going faster does not make more energy. It's just wrong, and it's kind of very stupid. And frankly, the pulley and the lever kind of prove the point. So this is bring up Steve Mould again, because he illustrated, frankly. He put a minute physics clip in demonstrating that pulleys conserve momentum. That is, a 1v motion here creates a 2v motion over here, and they're claiming that levers don't conserve momentum. So something as elemental as a lever, 2,000-year-old law of the lever, and they say it doesn't happen. I can't put a 2 mass and a 1 mass and call those an equality. Now, even though it balances perfectly, even though it's called a balance, because you can balance things, you can make a scale that's really quite accurate using it, the principle. They're claiming the principle doesn't work. All those scales are lying, because this 1.4 thing has to happen. I mean, it's a dramatic, a bold contradiction. It's just idiotic. To sit there and say, I'm going to do this silly rubber band crap experiment and prove, okay, the 2,000-year-old concept isn't true. The concept that has, by the way, made transmissions and gears and all kinds of machines that work perfectly efficiently because they do conserve momentum. And they don't do any of this. Yeah, it doesn't happen. You can't make free energy. Oh, fuck. What the hell just happened? Sorry, computer. It's just, yeah, it's doing things that I don't want it to do. But anyway, I will live and learn, hopefully, and it won't be too painful. But that's all, I'm just right there, right here. If they're going to say, yes, pulleys conserve this 1 to 2 velocity relationship, how can they possibly defend saying levers can't do that? They can't conserve momentum. How can they think that's true? All right. They've got to know that obviously their experiments are flawed, because they can't prove this to be true. And they can't prove this to not conserve momentum. And, trying to prove that this doesn't is just... Like I said, I like experiments. Do more. But again, they're not trying to get to the truth. They're trying to force results. Do it enough times in enough rickety ways until you get it to come out your way. That's what Professor Lewin did with the clay. He just manipulated the carts until the experiment worked. All right. Worked in the sense of coming up with the nonsense results. Okay, so enough said. So, the saga. I mean, really, this is the, if let's just say I'm right, okay, about all this stuff. So just for a minute, just bend your imagination. Just imagine that I'm right. Can you imagine the documentary of this story? What's the story? I mean, I'm making these clear, obvious challenge. Go ahead, show me. Show me this. Somewhere. Just show it to me and the argument is over. Show me with some kind of evidence that has some kind of integrity. Mythbusters crash cars. I don't think you have to do that. They could have engineered a better experiment. But don't you think there should be somebody engineering those better experiments to get to this truth? If you're going to claim it's true, you should prove it's true. Jesus. So all this, 10 years of this, and what's the reveal? You just don't want to hear that your fable isn't true. And why don't you want to hear it? So this is almost like that whatever he's called, Weinstein guy, Eric. He's basically saying we need a new physics because we need to get off the Earth. Oh, come on. It's just so silly, right? We need to move 8 billion people to some other planet. Yeah, oh, sure we do. We don't even, even if we could, like in Interstellar, solve the gravity problem, whatever the fuck that could mean, you really can't build a building that holds 8 billion people. So I just, love to see who gets a ticket, Do Muslims get to come? I mean, it's just... So yes, we need new physics because we don't like that we've soiled the planet and therefore have to go find some new thing to make a mess on. I mean, it's just so funny, frankly. But you still have to make food. I mean, how do you make food when you fly out to Saturn? So you don't even have solar energy anymore. What do and if you can make food, without doing the growing it someplace, and just synthesize it, well, why can't you do that on Earth? I mean, even if you pollute the fuck out of it, you could still sit there and, make food, mix your chemicals, make your soylent green. It's just, people are just so fucking dumb and creepy and dishonest and creepy and yeah, insincere and creepy. Oh, you're all so fucking creepy. Little lying creepies. Eee. Really is a bug planet. You really just haven't grown up. Never recognized that having a brain means you have a responsibility to use it well. It's a terrible thing to waste. Yes. Alright, anyway, till the next time, fuck you and such.